Hello everyone, welcome to Chapter 9. We have 4 main topics in this chapter. Our first topic is wireless network basics, our second topic is Cisco wireless architecture, our third topic is security and wireless network, and finally I will show you how you can create a wireless network on a wireless LAN controller. In this lesson we will cover the basics of the wireless network. First we will introduce to wireless technology, wireless LAN topologies, other wireless LAN topologies, an overview of radio frequencies. Then I will tell you about the wireless band and channels, and finally we will finish this lesson by explaining the access point and wireless standards. Now let's start with the introduction to wireless technology. Transferring a wireless signal works in a very similar way to a simple Ethernet hub. Both use the two-sided communication model. They use the same frequency to send and receive data. As we described in the previous sections, we define it as half-duplex. Wireless networks use radio frequencies emitted into the air from an antenna that generates radio waves, which can be absorbed, refracted, or reflected by water, walls, and metal surfaces in such a way that the signal strength decreases. Because of these environmental factors, wireless networks will never be able to provide the same service as wired networks, but this does not mean that we will not use wireless networks. Of course we will use wireless networks, as if there is no life without wireless today. Our mobile phones, computers and other devices are connected to the internet through wireless networks. There are various agencies that regulate wireless network standards and frequencies. You can see them in our table here. IEEE is an institution established to create and provide ready-to-use standards. Then there's the FFC, which is an institution created to regulate the use of wireless devices in the United States, and ETSI in another institution. This is also an institution that is authorized to improve the standards in Europe. Wi-Fi is an institution created to test Wi-Fi standards. LANA is an organization created to develop and teach consumer awareness about wireless networks. Let's talk a little about wireless LAN topologies on this page. We have said that wireless communication is carried out over free space using radio frequency signals. The theory behind radio frequency signals may be complicated, but I will tell you in more detail in the following sections. For now, suppose the transmitter of one device sends RF signals to the receiver of another device. A device here sends radio frequency signals to a device here, but there is only one-way communication here. We can give an example of radio. Think of this place as a radio station. Think of this place as your radio. The radio station sends the radio broadcast and you receive this broadcast from your radio. It is a one-sided communication, but in order to take full advantage of wireless communication, it must be both transmitter and receiver, as shown here, so that we can make the right use of wireless communication. Now if you want to take a look at the devices here, devices A, B, C and D, we have 4 devices. Imagine that our devices here are all using the same frequency and trying to send data at the same time. Then as you can see here, interference and fluctuations will occur and the signals will interfere with each other. The 802.11 standards used by these devices have been established to prevent these signals from interfering. When devices that use these standards send signals, they send signals by waiting for each other, because the structure here works half-duplex, so the signals should not all go to each other at the same time. So 802.11 standards have been established, since wireless devices are manufactured according to these standards and when they are connected to the network, this signal complexity is avoided. Now let's talk about the basic service set. In order to avoid the complexity we just mentioned, we gather our devices around access points so that all our wireless devices connect to access points. This gray area covered by access point is called the BSS basic service set. Users in a basic service set can communicate with each other, but not in this way from here to here, from where they send the signal to the access point, which transmits it to the other wireless user. In the same way, it transmits the signals it receives from the other user to the user here. Here access point organizes users here using a BSS wireless coverage area. Let's look at the distribution system on this page. For example, there is an access point and a wireless device. These wireless users who gather around the access point communicate with each other through the access point. But not only do they have to communicate with each other, these wireless users on the access point also need to connect to our wired network. To do this, we connect this access point to our switch with a cable so that they can access our wired network and the internet. We broadcast SIDs on a BSS above this access point, and below those SIDs we broadcast a MAC address, which is the BSS ID. A SID is issued for each SSID. As you can see in the figure on the side, we publish multiple SIDs on an access point and a BSS ID is published within each SSID. Here we have the first SSID in the light gray area, we have the second SSID in the middle, and we have the third SSID in the dark gray area. A total of 3 SIDs are currently published on this access point. It's called My Network, it's called Your Network, it's called Guest. Guest users here use VLAN 30, those here can use VLAN 20, and those here can use VLAN 10. In this way, we can separate the traffic of the users on the access point. Here, we can make our port between the access point and the switch a trunk so that different VLAN users on this access point can access the network. Let's look at the extended service set on this page. In this example, there are two access points. Where is the BSS area of the first access point? Where is the BSS area of the second access point? The coverage area of the first access point is limited to the gray area that we see here, but this user can move out of the range of this access point and into the coverage of another access point, because this user can move around. In this case, the user who is in the range of the other access point tries to connect to this device, then we set the SSID names here and the SSID names here the same. When we make these names the same, we expand our basic service set field here and create the extended service set field. On this page, let's talk about the other wireless topologies, repeater and workgroup bridge. Let's start with the repeater first. The coverage area of the access point you see here comes up to here, but this signal cannot reach our user, so this user is out of range. Then we provide access to client B by putting another access point where this signal ends and amplifying this signal by putting this access point in repeater mode. So we've extended the coverage area here by putting a new access point where the access point's signals end, so the client B can now connect to the wireless network. Let's look at workgroup bridge. Let's say our access point is the coverage area. This user in this coverage area can access the wireless network, but let's say we have a tomography device or a desktop computer that doesn't have a wireless connection. We use a method called workgroup bridge to connect these devices to the wireless network, and in this method, we use a device to connect the wired device to the wireless network, and with this device, we use our wired device to the wireless network we're connecting. Here, let's look at the outdoor bridge method. If the outdoor bridge is the access points, we put two access points between the buildings and connect these access points to the switch. The access point bridges the traffic it receives on this network to the access point here and from there to the switch. And when you make the port where the access point is connected to the trunk in this switch, it is as if you have connected this switch and this switch to each other by cable. So you can connect two networks to each other with access points. You can also do this method in a point-to-point manner. You can see an example of this here. Here you have your headquarters, here you can do LAN B, here you can do LAN A. You can also do it in a single-point multipoint format. Now let's talk about mesh network. If you don't have the ability to run a cable to access point, you can use such a topology, which is not a very useful topology, but you can use it when it is mandatory. In this structure, we pull a single cable from our switch and connect it to the access point and take the other access points to mesh mode and connect them all together in a daisy array. These access points use a separate channel to mesh among themselves, and users connect to the access point through a different channel. As I said, you can use it in cases where it is mandatory, but normally we draw a cable to each access point and connect them directly to the switch, because all of the access points here connect to the switch through a single cable and connect to each other wirelessly, but because they are connected to the switch with a single cable, our bandwidth is very low, so I recommend using this method only when it is mandatory. Now let's make an overview of radio frequencies on this page. We apply an electrical signal to one end to send data on a wired connection and we carry it to the other end. Since the wire of the cable is continuous and conductive, the signal is easily transmitted, but since there is no physical way to carry the signal in a wireless connection, the antenna that sends the radio frequency can send an alternating current by emitting moving electric and magnetic fields that propagate out and away as moving waves. The electric and magnetic fields move together, allowing the signal to be constantly altered or turned up and down to ensure that it always rides at a right angle to each other and is pushed outwards. As you can see in the figure here, electrical signals repel each other to form waves. These electromagnetic waves do not travel straight, but instead are transmitted by expanding from the antenna in all directions. That is, they do not travel in a straight manner as shown in the figure here. The signals travel as they expand into waves. The nearest signal is stronger. Here it shows the propagation of the signal. Here we have our receiver. Here we have the device that sends the signal. It sends the radio frequency by emitting waves around it. On this page, let's look at the loops within the wave. As the electromagnetic waves reach the antenna of the receiver, they form an electrical signal. We can measure the electromagnetic waves in a wireless connection in several ways. It is the frequency of the wave, or the number of times the signal cycles up and down in 1 second. In the figure here you can see how a wave cycle is defined. Here, when the signal rises and falls from the center line and rises again, a cycle begins, and the interval from the peak of one center to the peak of the other center is measured as a cycle. The portion from a peak to a peak can be measured as a cycle. No matter where you start measuring a cycle, the signal should make a complete sequence back to the starting position, where it is ready to repeat the same cyclic pattern. In the table here you can see the values in radio frequency, hertz, kilohertz, megahertz, gigahertz. 1000 Hz makes 1 kHz, 1 million Hz is 1 MHz, 1 billion Hz is 1 GHz. In this table, you can see the frequency spectrums of radio frequencies. We use the 5 GHz and 2.4 GHz bands in our wireless networks. Let's talk about wireless bands and channels here. As I said, we usually use the 2.4 GHz and 5 GHz bands in our wireless devices. In fact, we don't really use the 2.4 GHz bands between 2.4 GHz and 5 GHz, but we usually call it 2.4 GHz. There are a total of 13 channels that we use in 2.4 GHz. We use 13 channels in Turkey, but there are also countries that use 15 channels. For example, Channel 1 broadcasts in the 2412 GHz band, so it uses this frequency. Our 6th channel broadcasts using the 2437 frequency. It uses these channel ranges of our access points. If you are using 2.4 GHz, you will use channels 1 to 13. In 5 GHz, as you can see here, for different ranges are used, frequencies between 5150 and 5250 and 5250 and 5350, but we usually call it the 5 GHz band. In short, we use the 2.4 GHz and 5 GHz bands in our wireless networks. Here you can also see the channels we use in the 5 GHz band. Let's talk about access point and wireless standards on this page. Wireless devices and access points should all work in the same band. For example, if we have a wireless phone running 5 GHz, our access point should also work on the 5 GHz channel. The IEEE makes the wireless network standards. We use the standard. You can see the 802.11 standards we use in our wireless devices in the table here. Our first standard, 802.11, was published in 1997 using the 2.4 GHz band, with a top speed of 2 megabits per second. Then 802.11b was standardized, which was standardized in 1999, the highest speed of which was 11 megabits per second. Our next standard was 802.11a, which broadcast on the 5 GHz band and supported 54 megabits per second, which was removed in 1999 but did not become very popular because it was on the 5 GHz band and the majority of devices on the market supported 2.4 GHz. Then in 2003 they released 802.11g, which supported 2.4 GHz and likewise provided 54 megabits per second speed, after which in 2009 the 802.11n standard was approved, which was a nice standard that worked on both the 2.4 GHz and 5 GHz bands, which could reach speeds of 600 megabits per second. In 2013, the 802.11ac standard was developed, which broadcasts on the 5 GHz band and speeds of 6.93 gigabits per second can be reached. Most recently in 2019, 802.11ax was standardized by the IEEE, while 802.11ax broadcasts on the 2.4 GHz and 5 GHz bands and can reach speeds 4 times faster than 802.11ac. Since our codes here are a bit complicated and hard to keep in mind, the IEEE has given a number to these Wi-Fi standards we use. They identified 802.11ax as Wi-Fi 6. They called the 802.11ac standard Wi-Fi 5, the 802.11n called Wi-Fi 4, and the 802.11a and 11g standards called Wi-Fi 3, which is called Wi-Fi 2, which is called Wi-Fi 1. Nowadays, Wi-Fi 4, Wi-Fi 5 and Wi-Fi 6 are widely used. That's all we have to say in this lesson, so goodbye to see you in our next lesson. Hello everyone, I will talk about Cisco wireless architecture in this lesson. First we will talk about autonomous access point architecture, then we will compare split MAC access point architecture, cloud-based access point architecture and wireless controller types, and finally we will finish our lesson by talking about Cisco access point modes. Let's first look at the autonomous access point architecture. What is the first task of an access point? The main task of an access point is to provide data from wireless devices to the wired network, which acts as a bridge between the wired network and wireless clients. Autonomous access points can operate independently on their own, creating multiple BSS and different SIDs, allowing them to work across LANs. In the figure here, we have access layer level switches. We connect our access points, our phones and our end users to the switches here. When we connect our access point here to our switch, we make our port between the switch and the access point a trunk, and when we make this port a trunk, we can communicate with the VLANs on the switch. We can create different wireless LANs on the access point here. For example, we can take the first wireless LAN to VLAN 100 and our second wireless LAN to VLAN 200 and access different VLANs to our wired network on an access point with different SIDs. When we look at the figure here, each of our switches has access points and access points have SIDs on them, and through the SIDs, we enable our wireless clients to connect to the wired network through the switches. Here, our access point enables wired and wireless clients to communicate. We call access points autonomous access points that work alone without the need for any wireless controller. Let's look at the split MAC architecture on this page, and in split MAC, we outsource some of the features of autonomous access points to the wireless LAN controller and some to the access point. Previously RF management, association and roaming management, client authentication, security management and QoS, RF transmit, receive, MAC management and encryption on the autonomous access point were all done by the autonomous access point alone. In the split MAC architecture, we take the administrative features on the autonomous access point and make the wireless LAN controller do it. Other real-time functions continue to be done on the access point itself, and since we give the administrative features of the autonomous access point to the wireless LAN controller, we call the access points here lightweight access points. This access point performs functions such as RF sending and receiving and sending, MAC address management and encryption on its own, and the rest of the features are done on the wireless LAN controller. Here, we make the port between the access point and the switch access instead of the trunk. The CAPWAP tunnel is established between our access point and the wireless controller here. The different wireless LANs that we will create on the access point communicate with the wireless LAN controller through the CAPWAP tunnel. If you are using an autonomous access point, you do not need a wireless LAN controller. It can work alone and run all these features on itself, then you need to manage all the access points one at a time, but if you use the wireless LAN controller, you can manage these features collectively in the wireless LAN controller, and only these features work on the access points. This is how the split MAC access point architecture works, my friends. Let me tell you about CAPWAP tunnels on this page. CAPWAP Control Messages Tunnel, which is used to configure and manage the operation of access points in CAPWAP tunnels, is created. Access points are verified and encrypted through this tunnel. Access points are verified and managed securely by wireless LAN controller after they are verified. In a CAPWAP data tunnel, data packets to and from wireless clients are transported, but are not encrypted by default. And when data encryption is enabled on an access point, these packets are protected by the datagram transport layer security protocol. This figure shows the use of the tunnel. UDP port 5246 is used for the CAPWAP control tunnel. UDP port 5247 is used inside the CAPWAP data tunnel. These tunnels are established via the switch between the wireless LAN controller and each access point. In this way, it shows how to use the tunnel with LANs. Here we have the wireless LAN controller. Our access points are connected to the switch here. We set our ports between the switch and the access point as access port. The access point and the wireless controller create CAPWAP tunnels through the switch here and carry the data and control messages through this tunnel. Let's look at the cloud-based access architecture. In the architecture here, we connect the access points to our switches in the same way in our network, but there is no wireless LAN controller in our network here. We manage these access points in the cloud, that is, in the internet environment. Cisco Meraki's dashboard has a graphical interface that you control over the internet. Your data traffic here comes from here to the switch, from the switch to the core switch, and from there to the internet. Here, only the management traffic of the access points goes to the dashboard. The rest of your traffic goes to the internet from here, so your data does not go to Cisco Meraki and from there to the internet. With this model, you don't use any wireless controllers. You connect access points to your network and you can manage your access points from anywhere. Let's take a look at the comparisons of the types of wireless LAN controllers on this page. This is the deployment model called Unified, where we use the wireless LAN controller, in which there are one or more wireless controllers on the network, and the access points are managed by connecting to this wireless LAN controller. This model supports 6,000 access points and 64,000 users. There are more devices than this number, but here it is stated as 6,000. Let's look at the cloud-based wireless LAN controller model here. The only difference from the unified model is that the wireless LAN controller is not in a local network but in a remote data center. In the cloud deployment model, it can support up to 3,000 access points and 32,000 users. In the Mobility Express model, you can designate an access point as a wireless LAN controller and manage up to 100 access points and up to 2,000 users through this access point. The newly released Cisco lightweight access points also have Mobility Express software. If you are not going to use these access points with the wireless LAN controller, you manage other access points through this access point by installing the Mobility Express software and choosing one as the wireless controller, a suitable option for small businesses. In this model, we use the wireless LAN controller on our switches. We can manage it through the 9800 and 3850 series switches. If we use this model, we can manage up to 200 access points on our switch, which you can use in medium-sized locations. On this page, let's talk about access point modes. Let's talk about local mode first. Lightweight access points work in local mode by default. When not transmitting, access point scans other channels to measure noise level, measure interference, find fake access point devices and detect intrusion detection events. In monitor mode, the access point does not transmit at all, but allows its receiver to function as a special sensor. In Flex Connect, a CAPWAP tunnel cannot be established if an access point wireless LAN controller in a remote location cannot access it, so this access point must set the mode to Flex Connect. If configured as such, it can natively move traffic between the SSID and the VLAN through the switch. If we put access point in sniffer mode, access point then forwards the traffic it receives from other wireless devices to network analytics software such as Wild Packets, OmniPeak or Wireshark, with which we can do further analysis. Rouge detector mode is the mode we use to detect fraudulent devices by comparing the MAC addresses advertised on a wired and wireless network. Bridge mode creates a point-to-point or single-point multipoint bridge between access points, while the two access points in bridge mode are used to connect two locations separated by distances. For this, we have given an example before that we can connect our network by putting access points between two buildings. You can enable Flex Bridge mode to mesh on an access point. In SA Connect mode, we can use all channels of the access point to perform spectrum analysis and discover sources of interference. That's all we're going to tell you in this lesson, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will tell you how you can ensure the security of wireless networks. First, I will explain how to secure our wireless network, then I will talk about authentication, privacy and integrity methods. Then we will finish our lesson by talking about WPA, WPA2, WPA3 methods. On this page, let's start with the anatomy of a secure connection first. Normally in our wired connections, our users are connected directly to the switch and what they send goes directly, but in our wireless connection, the users are connected to the access point and our signal goes by radio frequencies over the air. Our wireless network here may involve strangers whom we do not want and can monitor the passwords and data we receive on our network. So security is very important in our wireless networks. We do not want to take unwanted people to our network. To do this, we first ensure that the user connects with authentication. Our user is connected to the network, but other people who know the password can also connect to our network. Then what we need to do, we need to encrypt this user's data. We have encrypted the data, but again, the users who know the password here and connect to the network may try to interfere with the data we have encrypted. Then we need to use integrity here. On a wireless network, we need to use authentication, privacy and integrity at the same time. Now let's continue our lesson by talking about authentication first. There are several methods that we will use to authenticate. One of them is to distribute a password to users on access points so that everyone can access the access point with that password. And the second method is to give our users a username and password using an identity server and then ask them to verify their identity from the identity server, and then we can use these two methods and we will look at the details of these in a moment. Now let's look at message privacy. At the moment the data between our user here and access point is not encrypted. Since we are on the same network as other users who know the password here, the bad guys here can still monitor the outgoing incoming traffic between us and the access point. So we need to encrypt our outgoing incoming traffic here. I will talk about these methods. Our third security method is to check whether there is interference with the traffic from the user to the access point by using integrity methods. To achieve this, we put a stamp on the beginning of our original data and encode this stamp and transmit it to the access point, and the access point compares the stamp, and if there is no change, it extracts the original data and transmits it to the other user. In the figure here, it shows how the transactions are done. We just talked about authentication, privacy and integrity methods. Now let's look at some more details here. First of all, let me tell you about open authentication. This method comes across to all of us in daily life. When you go to airports, cafes, shopping malls, when you connect to a network there, a web interface opens to you and asks you to confirm your credentials from this web interface, but since there is no encryption between the client and the access point, it informs you that your wireless data will not be secure in any way when you join this network. This method is often used in hotels, cafes, shopping malls. You are allowed to join the right by asking you for a password from the web interface. Our next method is web. As you can imagine, because open authentication offers nothing that can hide or encrypt the data sent between a user and an access point, alternatively the web standard has been defined as a method of making a wireless connection more similar to a wired connection. In this method, the RC4 encryption algorithm is used to encrypt each wireless data frame. Web keys can be 40 or 104 bits long, normally represented by a string of 10 or 26 hex values. This method was defined by the 802.11 standard in 1999, but in 2001, work began to find better wireless security methods due to a number of weaknesses, and in 2004 this method was officially deprecated. The next method is to use an 802.1x authentication server. In open authentication we did not ask for any password, we connected by entering a password in a web interface to connect to the access point, so when we connect there is no encryption between the users and the access point. In the web method, we gave users a password we had previously determined and enabled them to connect with this password. In this method, we use a server for authentication, and when our user is going to connect to the access point directs it to the identity server through the wireless LAN controller and asks that user to authenticate, which is how the 802.1x method works. Now let's look at the LEAP method, which is a method that Cisco developed. Cisco developed a wireless authentication method called LightweightEAP to close the weaknesses in the web method. In this method, the user must provide the username and password information to authenticate. On this page, let's first look at the EAP fast method, which in order to provide more security, a TLS tunnel is established between the authentication server and the authenticating device, and authentication is provided through this tunnel. If you want to learn more about these topics and learn how to set up and manage Cisco Wireless LAN Controller, you can then join my Cisco Wireless LAN training to learn how to design and set up wireless networks. Now let's look at the PAP method. Let me explain this method through the figure again. In the PAP method, our authentication server has a certificate from a certificate authority. Users already have information of major certificate authorities on their computers and mobile phones. For example, there are certificate authorities such as VeriSign, GoDaddy. These certificate authorities' root certificates are already installed on our devices. We import and install certificates from a trusted certificate authority on our authentication server, and the communication between users and the server is encrypted with these certificates. These methods are often used in corporate firms. In small companies they are not used much. All of these methods work with authentication servers such as Radius Server or TSACS Server, or if you want, Cisco has a product called Identity Service Engine that works as an authentication server. In this product, you can do your checks with this product. Let's talk about EAP-TLS on this page, and to explain this method, let me explain it on the way it was on our previous page. When we used the PAP method, we were getting and installing a certificate for the authentication server, but we were not installing any certificates on the user side, because the previously known and trusted certificates were installed on the user-side computers. The users communicated with the server's certificate because they trusted the certificate authority installed on the server. But in the EAP-TLS method, you have to get and install certificates for both the server and all your users. This method is an advanced security method. The EAP-TLS method also works in this way on a certificate-based basis. On this page I will tell you about the privacy and integrity methods. First let's look at the Temporal Key Integrity Protocol. This protocol was a method used in conjunction with web authentication. The message transmits our message by putting a stamp on our messages using integrity check, then adds a timestamp with the message integrity check to prevent attacks that try to reuse or recreate previously sent frames. TKIP Sequence Counter. This feature keeps track of the frames sent by the MAC address to prevent tampering with the frames. The key mixing algorithm calculates a one-time 128-bit web key for each frame, using these methods to secure web authentication. But since new methods were developed after 2004, web and TKIP methods are not used much today. CCMP is a protocol developed with the idea that it is more secure than TKIP, and this protocol uses two different algorithms. It uses AES counter mode encryption and CBC MAC algorithms. AES is used as the advanced encryption standard, which is the most widely used encryption method today. To secure a CCMP wireless network, client devices and access point hardware must support AES counter and CBC MAC. CCMP works with WPA and WPA2. The GCMP method is used in conjunction with WPA3, which is a more advanced version of CCMP. This uses AES counter mode and Galois messages authentication code. On this page, let's talk about WPA, WPA2 and WPA3, and in our previous sections we have covered various authentication methods, encryption and message integrity algorithms, but when we design our wireless networks, we need to know which one will work well or which one will work well together on our network. We need to know which authentication method is compatible with which encryption algorithm. This complicates our work. To make it easier, Wi-Fi Alliance, a non-profit wireless industry association, has combined them under the Wi-Fi Protected Access Certificate, that is, WPA has made WPA2 and WPA3 a standard, which message encryption algorithm you will use when you use them, and which message method you will use in the table here. If you use WPA, it supports pre-shared, it also supports 802.1x identity authentication. As encryption, it supports TKIP along with messages integrity check. WPA, it also supports AES and CCMP encryption, but not GCMP. WPA2 supports pre-shared key and 802.1x methods for authentication, but not messages integrity check and TKIP, but AES and CCMP. Our most advanced method, WPA3, supports pre-shared key and 802.1x for authentication, does not support TKIP and CCMP, an older algorithm, but supports more advanced GCMP. WPA, WPA2, and WPA3 methods make things easier when designing our wireless networks, determining which authentication method, privacy and integrity method we use, and limiting it. This is how you can secure the wireless network. We have to use them when designing our network, so we have to use authentication, privacy and integrity. If we don't use them, our wireless network won't be secure, and we use WPA, WPA2 and WPA3 to do these things, as I have shown here. Hello everyone, in this lesson I will tell you how to create a wireless LAN. First I will tell you how to connect Cisco access points, then how to connect the wireless LAN controller to our network, then I will tell you how to access the Cisco wireless LAN controller and how to create a wireless LAN on the Cisco wireless LAN controller. On this page, let me first tell you how we connect access points to our network. When we look at our figure here, if we are going to use autonomous access point in our network, we make our port between access point and switch trunk. If we are going to use a wireless LAN controller and lightweight access points in our network, we make our port between our access point and switch access port, and a CAPWAP tunnel is created between wireless LAN controller and access point, and our VLANs are these. We carry it through the tunnel. Since we are going to use wireless LAN controller here, we have made the port of our switch and access port. We can use the VLAN we use for wireless LAN controller for our access points. For example, if this wireless LAN controller is VLAN 20, we can also take our access points to VLAN 20. It can be in different VLANs, but it would be better if it is in the same VLAN. By creating different SIDs on the access point, we can use our users in different VLANs. Now let me first show you the ports that we use to connect the wireless LAN controller to the network. In the figure here you can see the Cisco 5508 wireless LAN controller. The port here is the service port. We use this service port for system recovery and first boot. We use this port on the switch side in access mode when connecting to the switch. Here it also shows how we can connect. If there is a VLAN that we use for management, we can get this port to that VLAN. On devices without this service port, we can access the device by giving a management IP to one of the normal ports. For example, I am currently using the 2504 series controller. This device does not have a service port, but I access the device through this port by managing one of the normal ports here. Now let's talk about the ports here. We call these ports distribution ports. In these ports we usually use them for access point and access point management traffic, and we usually make these ports trunks. If you are going to use link aggregation protocol here, i.e. Ether channel, you can use more than one port. There are 8 ports on this device. For example, you can make Ether channel by connecting 2 ports to the switch, but when you use a single port, you can connect it to your switch by making it a trunk. You can use the service port or not. You can access this device with the management IP over a single cable that you have connected here, but if you have a service port, you can connect it to a port of the switch and include it there if you have a management VLAN, and you can access it from there. Now we have connected the wireless LAN controller and access point to our switch and put our port in access mode. If you are using a single port between the switch and the controller, you make this port in trunk mode. If you are using more than one port, you can use the link aggregation control protocol. To access the wireless LAN controller, we open a web page and enter our management IP and come to this interface. When we enter here, this page first appears, and when we click on the Advanced tab from here, we reach this interface. I'm going to make our lab a little later, so I'm passing this place quickly. Then we will make a wireless LAN configuration. We will configure wireless LAN so that our users who connect to the access point can access the wired network. We will communicate our switch site networks, that is, our wired networks, with access point via wireless LAN controller. First of all, we will configure Radius server. If you do not have an authentication server on your network, you can go through this first step. I will show you these in a moment. In the second step we will configure the interfaces. If you do not have an authentication server, you can start without configuring the interface first. In the third step we will start configuring our wireless LANs, which I will quickly pass as I will show them in a moment. Then we finish our settings by configuring wireless security, and finally configuring quality of service, and finally we will set whether users connected to the Cisco wireless LAN controller graphical interface can access it over the wireless network. When we remove this, users connected from the wireless network will not be able to access the controller interface. We write the IP address we give to the service port of the wireless LAN controller or the IP address we give to the management port here. You can write here as HTTP or HTTPS. When we type our IP address, the login page opens first and we continue by saying login. Since I have entered the password before, I automatically come directly to the main page. Now from here we go to the advanced settings by clicking on Advanced tab. This is a new interface that we use to do our monitoring. We are moving on to the advanced settings page. Here you can see general information about our system, software version, name of the device. Here you can see information such as our date and time, whether the access points on it are working or not. Now we will first go to the security section and configure our Radius server. From the security tab we select Radius deauthentication under AAA. From here we add a new Radius server by saying new. If you do not have an authentication server, you can go through this step and start directly from the create interface step. I write the IP of our Radius server saying new 192.168.1.110. Here we also write a password. I made the password Cisco 123. This password we give must be the same on the server. When we press apply from here, our Radius server has been added. Let's apply again from here. Now we will create interface in the controller tab. Under the controller tab we click on the interface tab. Here by default there is the management interface. The IP address of this interface is 192.168.2.254. This is our interface in VLAN 20. I have already created interfaces for VLAN 30 and VLAN 40 here. Now let me show you how we added interfaces. Let's call it new and give interface a name. Our name is CCNA. Let the VLAN also be 50. Let's apply. Here we determine which physical port to use for this VLAN. We write 1 here since our first port is connected to the switch. Then we write our IP address for the VLAN. I write 192.168.50.254. Let's write subnet mask here. I write 192.168.5.0.1 as gateway. I write the IP of our DHCP server. Our IP address is 192.168.10.110. After typing them, we save our settings. Now that we've created our interface, let's come back here by doing back. Here you can see the interface that we have created. It will use VLAN 50 and its name is also CCNA. Now we can start creating a wireless LAN by clicking on the wireless LAN tab, where I have one wireless LAN that I'm using right now. It's called Cloud Network, and I'm connected through it. Now let's create a new one to test it. From here we say create new, we say go. Let's name it here CCNA Lab. Let the name of the SSID that we will publish be the same. We call it apply. From here we choose the interface we will use. You can see the interfaces I have created before. Guest, Employees and CCNA. We will use CCNA interface, that is, we will use VLAN 50. We state that we will use VLAN 50 for this SSID and we say apply. Now we come to the security section. WPA/WPA2 is already selected here in layer 2 security and we leave it here and come down. 802.1x default is also enabled here. If you are going to use Radius server, this place will stay this way. If you are going to use pre-shared key instead of Radius server, you choose PSK and give a password and distribute this password to users. Anyone who knows this password can connect to this network. Let me show you that first. Let it be Cisco 123. Once we've done that, we do apply. After giving our password, we need to make this SSID from here. When we activate here, 2 SIDs will be published on access point. Let's say apply and make our settings save configuration here. Our settings have been successfully saved. Now let me tell you a little bit about quality of service. Quality of service is a service that we use to select, prioritize and classify traffic in our network. If we use IP telephony in our network and we want the traffic of IP phone to be prioritized here, voice, when you prioritize the traffic of wireless IP phones, you already create a separate wireless LAN for it, and you create a wireless LAN here, you select voice in wireless LAN. I'm choosing silver best effort because we're not going to use voice here. Now that we have made all our settings, let's check our SIDs by clicking on the wireless LAN tab again. We are currently broadcasting 2 SIDs on this wireless LAN controller. Let's check our SIDs right here. You can see our newly published CCNA lab here. Now we can access the network through CCNA lab by entering our password. This is how we broadcast the SSID using a common password, so let me show you the Radius server. Let's get back into the CCNA wireless LAN. This time I enable 802.1x in the security tab and disable PSK. Let's apply. Now let's select the AAA server from the security tab again and select our Radius server here. Here, our Radius server stays at the top. Let's take out the others. Let's just leave the Radius server here, say apply, and save our settings. Our settings have been successfully saved. Now I come back to the wireless LAN. Right now you can see here that we will use WPA2 and 802.1x in authentication. Now let's do our test right away. Let's try to connect to CCNA lab. Now here asks for the username and password. Now everyone will log in with their own username and password. We no longer have a common password. In our previous method we set a password and anyone who knew the password could connect. In this method we use an authentication server and we make sure that each user in our network logs in with their own name and password. This method is more secure, which is how we usually use it in corporate companies. That's all we're going to tell you in this lesson, so goodbye to see you in our next lesson.